These five relationships, along with the definitions and the common notions, are the basis for all relationships that are proven in geometry. Okay, but there are five postulates. You need to know these postulates, and you need to know the order of them, 1, 2, 3, 4, 5. Okay, postulate number 1 is the existence of a line. Okay, so again, we're going down to the most basic first principle, so you have to assume that a line can exist. Okay? And what that means is if I have 2 points, points A and point B, the existence of a line allows me to validate that there exists a line that passes through these 2 points. Okay. So again, even though we can't actually prove it, we know that a line can exist, or that has to be accepted in order for the rest of the relationships to be built on that. Okay. In addition to existence of a line, we also have to postulate the extension of a line. And so what that means is if we begin with a segment, let's call it CD, and you have to postulate or accept the fact that we can extend this segment in each direction to form a straight line. Okay. So as far as what you need to know, the extension of a line, but this is kind of an illustration of that relationship. Okay. Postulate 3, in addition to existence of a line, we also have to postulate the existence of a circle. Right, and so existence of a circle says that given any point, we'll call that point E, and a distance, EF, you have to postulate the existence of a circle that can be formed with that information. Okay, so through given any center and a distance, EF, you have to assume that there exists a circle. For that, when you look at these postulates, there's a couple things. Again, these postulates, by being a postulate, they're based on geometric constructions. Therefore, they're limited to geometry. And not just geometry, but Euclidean or planar geometry. Again, these postulates may not be the case for different fields or branches of geometry, but for Euclidean geometry, they are assumed to be true. These first 3 postulates actually introduce our construction tools. Right? What do existence of a line, extension of a line introduce? Which geometric tool? Yeah. Therefore, it's limited to geometry. Okay, so postulate 1 and 2 actually introduce the use of a straight edge in your constructions. Postulate 3 introduces the use of a compass as a geometry tool. Okay, there's 2 more postulates that are, again, based on constructions, therefore limited to geometry. The 4th one is all right angles are equal. Okay, so what this one states is if you have a right angle here and a right angle that's oriented differently, these 2 angles have the same magnitude. Again, it's the one way that magnitude is introduced into Euclidean geometry. And because originally there was no measurement, so they didn't actually measure angles, they simply compared them to right angles. So because of that comparison, you had to assume the relationships or assume that right angles do exist and that all right angles, no matter how they're drawn, Okay, so whichever way they're oriented, it could also mean if one of them has smaller rays or sides than another. No matter what, those are all considered equal magnitudes. Magnitude is just the measurement. So this kind of allowed the relationship between what we call measurements to be made. Before, again, obtuse angles were simply classified as they related to right angles. An obtuse triangle is greater than a right angle. An acute triangle or an acute angle is less than a right angle. Right? A straight line is the sum of two right angles. So it allows you to introduce some magnitude in there. The final postulate is referred to as the parallel postulate. Again, you can refer to it in this sense. I'm going to go through and kind of talk through the wording of this. Sometimes the wording of it might be a little bit confusing. I'll give you the modern take on what it also stands to represent. But the parallel postulate says the following. If two lines are intersected by a third line, and the intersecting line is called a transversal. We'll get to that later. You don't need to know it right now, but just as far as introducing a term that we'll get to. Okay, but if you have two lines that are intersected by a third line, and the angles formed on those lines are less than two right angles. Okay, so what this is saying is if the measure of angle 1 plus measure of angle 2 is less than, what is two right angles again? 180. Okay, so basically this is just a long way of saying if you have these two lines intersected by a third line, if the two angles on the same side of that transversal or third line have a value or a sum that's less than 180, then the relationship that occurs is that the lines will converge on that side. Okay, so what this means is if angles 1 and 2 are less than 180, then the lines will intersect to the right. And what if angle 1 and angle 2 are greater than 180? What would that mean? Where would these lines intersect? On the other side, away from it. So in this case, to the left. And then that leaves kind of the final thing and the reason why it's called the parallel postulate, and that is, what if angles 1 and 2 are equal to 180? So they don't converge on the right, they don't converge on the left, so what's going to have to happen to them? They are parallel. So that's why it's called parallel postulate. And there's a kind of the more modern take on what parallel postulate represents is the following relationship. If you have a line and a point not on that line, the parallel postulate states there can be only one line that passes through this given point that is parallel to the given line. Okay, so only one line can pass through a given point that's parallel to a given line. Okay, we're going to come back and use this when we start doing proofs, and the portion of this parallel postulate that we will most likely use is this bottom relationship. If you intersect